Now, how were these amino acids linked together in a protein or a polypeptide? And the solution to this problem was really solved by two chemists at the same time. Emil Fischer, right, the guy who gave rise to Fischer projections and all the other aspects of organic chemistry that you know, and another guy by the name of Franz Hofmeister. Anybody heard of Hofmeister? Remember the Hofmeister series? That's him. So those two great chemists at a meeting at the Society of, I think it was the 74th meeting of the Society of German Scientists and Physicians, shows you how close medicine and science were linked, right? Sat down and came up with the way the amino acids were linked. And they recognized that, in fact, the amino acids were linked through a condensation reaction. What was happening, in fact, was that amino acid number 1, NH3 plus, plus amino acid number 2, underwent a condensation reaction. In order to form now, what kind of bond? What kind of bond is this? Peptide bond. What do we call it chemically? You're right, it is a peptide bond. In fact, it was Fischer who first coined that term, peptide bond. What kind of bond? Amide bond, right? That's why I said proteins were polyamides. It's an amide bond. Okay? Now, this is now called, we will call this in general at this point, a dipeptide. Because it's linked by a peptide bond. Okay? And now we're going to give a new name to these things. We're going to call from now on, we're not going to call this an amino acid anymore, but we're going to call this part and this part by new names. When they're linked together, we're going to call these residues, amino acid residues. It's what happens after the amino acid comes together to form the amide bond. Now, notice that this is a condensation reaction. Should you be concerned about it being a condensation reaction? Seems a little odd, doesn't it? Why is this problematic in life? Where does this reaction happening? In 55 molar H2O. What about Le Chatelier? How can these things condense in the presence of 55 molar H2O? Isn't H2O going to drive the reaction the other way? So where does the peptide bond happen? Does it happen in solution? Where does it happen? On the ribosome, of course. It doesn't happen free in solution. Okay? What happens to proteins that sit around long enough in H2O? What do you think in 55 molar H2O the equilibrium state is? Is it a protein or is it free amino acids? Free amino acids. So how come you're not all dissolving in front of me? That's the difference between kinetics and equilibrium. And we'll talk about that when we talk about enzyme kinetics. If you leave something long enough, like dead bodies, what do? They turn into free amino acids. Okay. Now, the next hero of 705 happens to be this guy. Anybody recognize him? Greatest chemist in my mind of all time. Linus Pauling, man, Linus Pauling, greatest chemist ever. What is it that Linus Pauling did? What are some of the things he did? Well, he worked on the geometry of peptide bonds. Okay. And in those days, he did it by X-ray crystallography, a fantastic technique that we'll talk about at length. And he measured bond distances and bond angles. what you're looking at here, right, is the crystal structure of a dipeptide. Here's one amino acid. Here's the nitrogen. Here's the alpha carbon. Here's the R group. Here's the carbonyl. Here's the amide bond to the NH group. Here's the next alpha carbon. Here's its R group. Here's the carbonyl. And he measured. One of the things you can do with X-ray crystallography is make very accurate measurements. And he noticed a couple of interesting things here. Well, he noticed, for example, that a typical carbon-nitrogen bond, this was known at the time, is somewhere on the order of about 1.45 to 1.49 angstroms. Right? That's this distance. You can see it's right here between carbon and nitrogen. Okay? And he knew that a carbon-nitrogen double bond, because those structures had been solved, that was on the order of about 1.27 angstroms. And he noticed something really interesting, which was that this bond, this amide bond, was 1.32 angstroms. It was somewhere midway between a single bond and a double bond. And why is that? Now it's the answer you gave me earlier. Why is that? That's resonance, right? Because, of course, what you have is this situation. You have the situation where the free electron pair on the nitrogen in the amide bond can give rise to this alternative structure. So this is resonance. Now, there's some important consequences of that. And they happen to do with the hybridization state of the nitrogen and the carbon. In order for this resonance form to exist, this carbon and this nitrogen have to both have partial double bond character. So, in order for that to be the case, what's the hybridization state? What's the orbital hybridization state of the carbon and the nitrogen? I heard it, sp2. These must be sp2 hybridized in order for that to occur. If they're sp2 hybridized, then that means I can draw something like this. I can draw carbon, nitrogen. This carbon's going to be bonded to an oxygen. Okay, and these are sp2 hybrids. And so I can draw the orbital off this carbon and the orbital off of this nitrogen, and I can even draw the orbital off of this oxygen. And these will all be shared, right, through two giant pi bonds. Now, the only way that can happen is if there's limited rotation around this bond. Limited rotation. Because if I start to twist this bond and move this angle, then those orbitals are no longer overlapping with the orbitals on the carbon. Okay? And as a result, this carbon, oxygen, nitrogen, hydrogen unit must be planar. And that's what's shown in that box there. It is a planar unit. You will see more of this when we talk about this a little bit later.